Okay. First of all, I want to thank you. I want to thank Jose Miguel. He's not here in the moment, but Javier. Okay. Thank you, Jose Miguel, for inviting me over, and Javier. And I will basically speak about asteroids and what we can do with CanariCam, and a little bit also what, in my opinion, we shouldn't do with CanariCam. So why we study asteroids in the thermal infrared? Because asteroids are warm objects, warmed up by the sunlight. And as you can see from this plot, these are the points are data points taken with the LWS at Keck when it was still available. And as you can see, the thermal infrared emission, the SID of asteroid peaks at around 8 to 10 micron, depending on their temperature. We're dealing with objects with temperature between 500 K to 250 K, depending on their distance from the sun and so forth. This is the flux, and this is the wavelength, and the lines are thermal models that we fit to these bodies, to the thermal emission, basically to derive sizes of asteroids. Yeah, the main reason why we want to observe asteroids in the thermal infrared is because we can easily derive sizes of these bodies. We use this basic formula, which relates the size of the asteroid to the albedo of the surface and the H value. H value is the visible magnitude scaled at 1 AU from the sun and 1 AU from the Earth, 0 degrees of phase angle. That's a simple, you observe with an optical telescope, and it's a simple geometrical calculation to derive H from the V magnitude measured at the time of the discovery. So the problem is that the time of discovery, the problem is you have the visible flux, so H, but the visible flux is proportional to the square of the diameter and the albedo. But because the albedo can range from 3% to 60%, the visible flux is a very bad measurement, it's a very bad estimate of the size. For example, if for H18, if you don't know the albedo, the diameter can be anywhere between half a kilometer and 2 kilometers, which is a huge error. On the other hand, the thermal infrared flux is proportional only to the surface of the body, and there's a very weak dependence on the albedo, so you can derive better sizes.
Doesn't that depend on the rotation rate?
It depends on the temperature, exactly. And the temperature depends on the rotation rate. That's correct, and we're gonna deal with that very soon. It's very important. So why we're interested in size? A little bit of scientific, science case. So basically, the size is the most important physical characteristic of our bodies, and it's the only. So if you have size for a statistical sample of object, you can study the size distribution in different population of asteroids, and this is important to constrain the collisional evolution of the bodies, the formation of these asteroids in the main belt, the transportation mechanism to the near Earth space, which are size dependent, and in the case of near-Earth asteroid, dangerous bodies, it's important to the assessment of the impact risk they pose for our planets. In the case of binary objects for which we have the masses of the system from the orbit, the size allow us to derive the bulk density and internal structure, which is the basic, very important unknown in asteroid science. If you have size, you can derive the albedo, which constrains the surface mineralogy and the origin of the body. As Charlie once mentioned, the thermal inertia is another important parameter that we can derive from thermal infrared observation. The thermal inertia is basically the resistance to temperature changes on the surface of a material. And it's a very important indicator for the presence or absence of regolith. For example, for Eros, this asteroid, we derived a kind of moderate thermal inertia, and we expected to find finer and thicker regolith, and this is what we find on the surface from direct imaging. In the case of Itokawa is a body that was visited by the mission Hayabusa, and an extent of campaign of thermal infrared observation were done, and we derived the thermal inertia much higher than this one, and which is consistent with coarser regolith and boulders on the surface. And indeed, which is what we found. The thermal inertia controls the temperature distribution on the surface of the asteroid. And this is important, for example, for mission planning. If you want to land on an asteroid, engineers ask you what the temperature we have to deal with. And then a very crucial thing is the Yarkovsky effect, which is the link between the dynamics of this body, dynamical evolution of these bodies, and their sizes. So dynamics and physical characterization are two separate worlds. Yarkovsky effect makes the link between them because this is the secular drift caused by the orbit, the variation of the semi-major axis, due to a propulsion of the photons emitted in the direction along the orbital velocity. Because of the thermal inertia cause an asymmetry in the temperature distribution of the body. That's it. And so thermal inertia causes the temperature asymmetry. This is the tangential force component that creates this Yarkovsky effect. It is size dependent. That's why it's important to understand sizes of this asteroid. And the Yarkovsky effect is crucial to understand the delivery of the origin of near-Earth asteroids, and it's also the major source of uncertainty in the impact risk calculation of dangerous asteroids, such as this one, 1950 DA, and the famous 1999 42 Apophis. So I want to give a little overview of where we are now with this kind of studies. We know about 2,200 sizes and albedos, mainly for main belt asteroids from old IRAS measurements. So we know about more than 350,000 asteroids, and we have sizes only for this number of bodies. These are kind of old measurements. These are kind of the accuracy we have in the size for objects larger than 100 kilometers, and the accuracy is much less and is poorer for bodies of smaller sizes. In the case of NEAs, we have only about 90 sizes, derived mainly from ground-based survey that we have done at the Keck, at ESO telescopes, and so forth. And we know about 5,000 NEAs. So we had to derive the statistical information about the size distribution from these only for this small sample. So one idea we can have is go to the CanariCam and get a lot of diameters and albedos of asteroids to improve our understanding of the population. I don't think this is a good idea, because very soon there are surveys. For example, in the case of near-Earth objects, there is a survey by PI Dave Trilling that awarded about 500 hours of warm Spitzer time when the past cryogen part of the mission to get thermal infrared measurements of about 700 NEAs. So it's not a good idea to just use CanariCam to derive sizes and albedos of this kind of bodies. 3 minutes only? Oh, okay. I'll go a little faster then. So in the case of main belt asteroid, there is another serendipitous Spitzer survey that will take about 35,000 asteroids. WISE mission. The WISE mission, I think, is gonna observe all asteroids that can be done with the CanariCam. Okay, that's enough. So what is left? I think what is left is a detailed, I think I'll skip this, is a detailed investigation of these bodies with CanariCam. Okay, one thing that we can do with CanariCam, I won't skip it, is to use detailed thermophysics, get observation at different times, for example, or accurate observation for objects for which we know the spin vector and sizes, and spin vector and shapes, and we can use more sophisticated thermal models that are not the case of this kind of large surveys. These thermal models from these thermal models we can derive the thermal inertia of the surface. The thermal inertia, as I said, is a very interesting indicator for the regolith, and I think I will finish showing what the thermal inertia tells us and what we need to do. So, for example, this is a plot of the thermal inertia of asteroids as function of size. And as you can see, the large main belt asteroids have low thermal inertia, whereas the near asteroids, smaller nearest asteroids, have higher thermal inertia. There's a kind of correlation between, an inverse correlation between size and thermal inertia. But the question is, so these bodies have coarser regolith, and these have much finer regolith. So the regolith is very interesting because it tells us about the process, the impact process that were going on the surface of these bodies, and how these bodies accumulated regolith. One of the problems is, are NEAs a proxy of small main belt asteroids? We don't know, but very recently, Lamy et al. Derived the thermal inertia for stains, the Rosetta mission target. It's in very good agreement with this, the NEA. So we're kind of happy. We say, okay, maybe the thermal inertia of NEAs is similar to the thermal inertia of small main belt asteroids. But more recent results show that this is not always the case. There are the Carine family members. These are objects between around 1.5 and 20 kilometers. There is an indication of very low thermal inertia. So there's like a dichotomy in the thermal inertia of small main belt asteroid, which is an indication that they have different surface and resurfaces processing going on. If I have one more minute, I want to show, I think, a cool thing that we can also do in the NEA with CanariCam. Study binary and slow rotators. These are normal NEAs, but if you look at the slow rotators, like Itokawa, 2100 Rashalom, and GU3, which is not really a slow rotator, but kind of almost 7.5 hour rotation rate, which is kind of low for NEAs. This Umberto got this thermal inertia. They look to have higher thermal inertia than normal NEAs. So do binaries NEA. Binaries tend to have a higher thermal inertia. And we think that the reason is because of a resurfacing process. This is something like a proxy. This is a simulation that show what's going on if we take an asteroid, a rubble pile, which is only gravitational aggregate, and we spin it up. The object tend to go to this kind of top shaped. This is the equatorial view, shed material on the orbit, and can eventually end up forming a binary system. So as you can see, the polar regions are devoid by regolith. Here is the binary, and the polar regions are devoid of regolith. So we think that binaries might have thermal inertia because of this formation process. I think I would skip this. Stains might be one of these objects because they have this kind of very cool top shape. And I'll finish with this. What about slow rotators? A lot of slow rotators, a large fraction of slow rotators appear to have bilobated shape. These are radar images. So they might be possible that these slow rotators and binaries have both high thermal inertia because they have a common origin. We don't know. Maybe these slow rotators, bilobated objects, they were once binaries formed by this formation process, which I didn't tell you what it is. It's York. It's basically a kind of brother of son of Yarkovsky, because the thermal emission does not only push the asteroid, they have a momentum, but it gives to the asteroid also angular momentum. So the asteroid can spin up or spinning down. I have no time to do this, but I think I'll leave with these conclusions. Thank you.
Marco, the observations that are going to be made with this, during the Spitzer War mission. First of all, I'm a little curious, what wavelength are they going to be?
Yeah, the wavelengths are around 4 microns, 3.6 and 4.5. Are the two, the first hierarchy, yeah.
I guess one of the questions then, there are two associated questions. One is, would it be useful to get observations from the ground that are simultaneous, even though you said, well, it's going to be observed with the War mission, for example, by Treeling and company. But it seems like if for no other reason than to kind of calibrate the ground-based observations.
Absolutely.
So that's one.
Yes.
Okay.
Yes. We put in, again, if there's somebody in the TAC, I can take a photo. We put in an ESO proposal to get a 10 micron band, 10 micron filter around here. Because as you see here, there's a strong contamination of the reflected light. So the thermal model is bad and get worse. Worse and worse has the object have higher albedo. So the higher is the albedo, the worse the accuracy of the diameter and albedo determination is going to be.
If you, the second part of that question is, okay, let's suppose you get the Spitzer-Warm and CanariCam or some other thermal observations at the longer wavelengths at the same time. Do you think that getting the spin vector and everything, knowing the spin vector for that the particular object and that information, later on, do you feel like if you then go back and say you observe the object in the mid-infrared with CanariCam, say 2 years later, do you feel confident that when you observe it that second time that you will be able to judge the configuration? Or is the system fairly stable? Once you know the spin vector and everything, do you think things evolve or change such that the second time you look at it, you would expect the configuration that you're seeing at 10 microns to match the configuration that you saw before? Does that make sense? Do you understand what I mean?
That's a very interesting question. I think we can separate it in two parts. The first part is that there are objects that they are observable now, but they won't be observable for the next 10 years or even longer. So you have to wait a long time to get a second, let's say, a second observation, a second epoch or a third epoch or something. These are typical objects that goes through a close approach, and then they won't come back for 20 years or something. That's NEOs. For those objects, the second part of the question is, for those objects for which you have or we can derive the shape and the spin vector, I would say yes, within 10 or 15 years, you can come back and get the second epoch. You can actually use it in a kind of confident way. And this is what we did with IRIS observation. It's very cool now because we have spin vectors that we didn't have at the time of IRIS observation, so we can revise somewhat in some respect the IRIS catalog. Yeah, you can do that.
Thank you very much.
You're welcome. Perfect. Do you need the mic? Yes, I think so.